the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. If you haven't noticed from my previous videos, I'm a huge fan of applying mathematics to real-world situations. To get a student to that point, however, requires a delicate balancing act between building background theory and bolstering confidence. The background theory is required to understand the why of the mathematics rather than the how. Why do we use this method rather than that, and why does this method work versus just tell me how this is done. The confidence bolstering is necessary to get the student to feel comfortable enough to use their computational knowledge outside of textbook situations. Ugly data and correspondingly ugly graphs exist throughout all fields and careers, and having the ability to work with these mathematically grants significant advantages when it comes to career options, supporting arguments, building proposals, and analyzing claims. One of the first skills necessary when working with applications is the ability to interpret the meaning of intercepts. Therefore, in this video, I will cover how to interpret the intercepts in an application, both from a graphical and a functional or equation perspective. So let's get started. I love to hike, and each spring break I hike roughly 80 miles on the Pacific Crest Trail over the course of about 5 days. The speed at which I hike depends on several factors, but one of the most important is the grade or the slope of the trail. The following graph shows my hiking speed based upon the grade of the trail. It's important to remind you that grade is just another word for slope. So a grade of 0.1 is a trail having slope 1/10. This means that the trail rises 1 foot for every 10 feet of hiking. You will often see roads with grade signs like this. This 10% is equivalent to 0.1, which is just a slope of 1/10. Interestingly, a lot of people get confused when they hear of a road with a 100% grade. They think this is a vertical road, but it's not. 100% is just equal to, mathematically, 1. Thus, this represents a road with a slope of 1. That is, the road rises 1 foot for every 1 foot of travel. That's basically a 45-degree angle. Anyhow, what are the horizontal and vertical intercepts, and what do they mean in this situation? Since this is a review video on the interpretation of intercepts, let's spend a little bit of time talking about what the intercepts are for any given graph. What I'm highlighting here is the horizontal axis. Most old school instructors would call this the x-axis, however, that is very limiting. And in this case, it's actually not true because I didn't use x to represent the variable for my horizontal axis. You'd be best to always refer to this axis as the horizontal axis, so you don't have to worry about what variable people might choose for it. In this specific example, because I used g to be the variable associated with the horizontal axis, you could call this the g-axis. Anyhow, anytime your graph touches this horizontal axis, we say that point is a horizontal intercept, or you could call it, in this case, a g-intercept. Likewise, this other axis I'm highlighting is called the vertical axis, or since I've chosen to associate the variable s with this axis, we could call it the s-axis. Just like with the intercepts for the horizontal axis, we say that a point is a vertical intercept, or s-intercept, if your graph touches the vertical axis at that point. Before I go any further, it's incredibly important to remind you that functions might not have vertical intercepts, or might have at most one vertical intercept. On the other hand, with regards to horizontal intercepts, they might not have any, or they might have one or more than one, or an infinite number of them. As for non-function relations, well, these might have more than one vertical intercept. This is a perfect example. All right, now that we've reviewed what intercepts are, let's get back to this application and interpret their meaning for this situation. We start by referring to a random ordered pair on this graph as the point g, s, where g is the grade of the trail and s is the speed at which I can hike at that grade. Starting with the vertical intercept, we can see that in this case, it is given by the point 0, 3. This means if the trail has a grade of 0, that is, it's just flat, then I can hike at 3 miles per hour. That's it. That's the interpretation. Notice I didn't respond with when g is equal to 0, s is equal to 3. That wouldn't be an interpretation. It's just restating something already given to us. Moving on to the horizontal intercepts, we can see that the leftmost is roughly -3, 0, and the rightmost is again roughly 1.8, 0. Recall that those first coordinates in each ordered pair represent the grade of the trail. As a percent, the leftmost again is roughly -300% grade, and the rightmost is a 180% grade. Both of these are incredibly steep, but what do they mean? Well, the leftmost means that if I'm going downhill and the trail is super steep at a -300% grade, I just give up. I can't move forward. I'd likely fall down the hill. Likewise, if I'm still climbing and the trail has a 180% grade, I just can't make any progress. I can't climb that steep hill. Again, notice I did not say it means that when g is equal to -3 or g is equal to 1.8, s must be 0. That is not an interpretation. If given a function representing a real-world situation or modeling data, you often are asked to evaluate and interpret intercepts. Instead of scouring the internet for cool functions, which I've already done honestly, and found that most were well beyond the scope of an algebra course, let's go ahead and consider the following. For this function, we are supposing there's a magnet 10 feet away from us. This function represents the strength of the magnetic pull in Teslas, not cars but units for the magnetic pull, based on our distance away from this initial point. Find and interpret the intercepts. It's important for me to note, d is the distance away from the initial point, not the distance away from the magnet. So d equals 0 means we are 0 feet away from the initial point, which is actually 10 feet away from the magnet. The vertical intercept is often the easiest to start with, so let's begin there. Letting d equal 0, we get p of 0 is equal to 1.3. Now what does this mean? Let's recall that the input represents the distance away from the initial point on the figure, which is 10 feet away from the magnet. So d equals 0 represents standing at that initial point, and therefore p of 0 is equal to 1.3 represents the magnetic pull at that point. So we experience a pull of 1.3 Teslas at our initial point 10 feet from the magnet. Now let's go ahead and find the horizontal intercepts. To do so mechanically, we let the output equal 0 and solve. In this case, we get that d is equal to -65. So if p is 0, then d is -65. Our drawing kind of helps here with the interpretation. We can see that this means we are standing 65 feet to the left, according to our drawing, of the initial point, or 75 feet away from the magnet. Therefore, our interpretation is that there's no magnetic pull when we are 75 feet away from the magnet. As an aside, theoretically, we should always have a trace pull from the magnet, but I didn't want to do an exponential function here. There are a couple of major mistakes I commonly see from students when asked to interpret intercepts. First, as I stated in the initial example, you should never respond with what is already stated. That is, given the intercept 0, 3, you should not respond with, the intercept means that x is equal to 0 when y is equal to 3. That's a worthless response and shows no understanding of the underlying application. Second, and this kind of ties with the first mistake, but it's a bit worse, I'll have students respond with, the vertical intercept is where the graph hits the y-axis. While this might be mechanically true, it is not an interpretation of the vertical intercept. In any case, when interpreting the meaning of an intercept, your answer should at least involve the units of the axes. If it doesn't, then your answer is definitely wrong. Thank you for watching this short review video on the interpretation of intercepts. As always, this content should be prerequisite to the course in which you're currently enrolled. If you found this material unfamiliar, or if it was confusing to you, then I recommend you click on the provided relevant prerequisite links listed below for further help. However, if you find you're continually doing this, you might want to consider speaking with your instructor about other course options. On that note, I sincerely hope these videos help you achieve success in your transfer level math and science courses. Cue the music.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.